enabling the digital economy.
So my program for the day is essentially three things. I would like to, first of all, open the box, unpack the quantum computer. I'm sure you all get exposed to media, press, articles and videos about how weird and spooky everything quantum is and nobody understands it, it's all mysterious. That's not true, okay? I don't have the ambition of teaching you quantum mechanics in 42 minutes, but I would like to demystify the complexity of it and the incomprehensibility of it. It's really not that odd. And then I will go into the actual meat of the presentation, which is to give you a sense of what a quantum computer is, how we build one, and a few examples of what it does and what it can be used for. And I will touch upon at the end and also throughout the talk my own personal activity here at the University of New South Wales in Sydney on building quantum computers out of silicon. But before we start, let's really begin from the core of the matter. What is quantum? What does that even mean, right? And the correct answer is that quantum is the description of the natural world that accounts for essentially a law of nature, a new law of nature, like Maxwell's equations, like Newton's equations are laws of nature. And it's called the Heisenberg uncertainty principle. And it says, what you see there on the screen, that the product of the uncertainty on the position and on the momentum, which is the velocity times the mass of a particle, must be larger than half the Planck constant, which is a constant of nature that's about 10 to the minus 34 joules second. Now, I don't expect this to mean anything to you, so let me give you a practical example. All right? So let's take a tennis ball. Let's say you're a tennis player. I'm taking an amateur tennis player who hits the ball at about 100 kilometers an hour, so let's say 30 meters per second. The ball is about 50 grams. So for a tennis ball, the Heisenberg uncertainty principle says that if you want to know its velocity to within 10 to the minus 16 meter per second, so 17 significant digits of precisions of that velocity, the uncertainty on where the ball actually is has to be 10 to the minus 17 meters, which means less than the size of an atom, in fact, less than the size of a proton. So this is the sense in which we say a tennis ball is a classical object, is not a quantum object. It's actually a quantum object too, but because of its size and mass, the quantum uncertainty principle doesn't matter. It's completely irrelevant. Let's take another example. Let's take an electron at the same speed. The electron is much, much lighter than a tennis ball, of course. So if you want to know its velocity to within 30%, so a 10 meter per second uncertainty on the velocity, you need to have a 10 micron uncertainty on its position, which is much more than its own size, which means basically you have no idea where it is. So in this sense, an electron is a quantum particle. It's the same law for the tennis ball and the electron, but for the tennis ball it doesn't matter. It's irrelevant. That uncertainty is so small that it doesn't matter. For the electron, it completely rules its world. So because of this uncertainty, you get funny effects which are completely natural, such as superposition effects. So now imagine you have an electron gun, you're shooting electrons, like the gun that shoots tennis balls when you're training, right? But it does it with electrons. And then you have a screen with two slits, and those two slits are less than 10 microns apart. Okay? Where does the electron go, the left or the right slit? Well, you don't even know where it is to better than the distance between the slits. So the only logical answer is that the electron goes through both slits. That's all you can possibly say. And then when you look behind the screen, there's going to be an interference pattern that looks like the pattern of a wave. So that's what you would have if you tried in your own bathtub to make a cardboard with two slits and drop a stone. You'll get two waves that go towards the slit, and you'll see an interference pattern behind the cardboard double slit. Now, you can actually see these electron waves with certain tools that are themselves quantum tools. This is a scanning tunneling microscope experiment of the surface of a piece of copper, which is a metal that has free electrons everywhere, where they've made a corral of iron atoms That coral confines the electron waves inside it, and so you can actually see this ripple, this wave of probability of the electron being confined by this coral. This is actually a fantastic, modern technique to see the quantum world and its wave nature. Now, because of superposition has a lot to do with symmetry. So let's say you have two protons, two positive charges that are identical, and you have one electron. Okay? So the electron is a negative charge, would like to bond to the proton, to the positive charge. Now, which one does it choose? Does it choose the left one, or does it choose the right one? What do you think is the logical answer? Both. Why on earth would it choose one of them? The logical answer is that it will be in a superposition of being left and right. There is nothing weird or odd about this. It seems like you all agree with me. I'm very happy. Okay. And so that the image you see at the bottom is a sort of representation of the electron probability distribution around a pair of protons in a hydrogen molecule, for example. Let's look at another example of a quantum particle. That's the spin. Every fundamental particle has a spin, so protons, neutrons, electrons have a spin. Spin is essentially a microscopic magnetic dipole, like the needle of a compass, but really, really small at the microscopic scale. And so it produces a small magnetic field. And you may wonder, can we see a spin? Can we actually observe the magnetic field produced by the spin? And if you've ever had the misfortune of needing an MRI scan in hospital, you would have seen the concentration of proton spins inside your body. So this is an MRI scan, and what you see, the light contrast, means that there is a high density of proton spins in there. So you can actually see it, and it's a diagnostic medical tool these days. But that's a lot of spins. Can we see a single spin? This is hard, but it can be done. And I'm going to show you an example from my own laboratory here. So this is a device that was made by one of my students. And the colors are fake. They're just for presentation purposes. But this is basically a silicon transistor. It may not look like one, but it's a modified silicon transistor. The yellow strip is a microwave antenna, kind of like the super high frequency and nanometer scale version of this antenna here. And then next to that transistor, which is colored in red, we implant a single atom of phosphorus. Phosphorus is an atom that, when placed in silicon, captures an extra electron, which itself has a spin, and also the nucleus itself of the phosphorus has a spin. So you get a two-spin system in there. And now this is a video. It's an animation that's been made by a student of the College of Fine Arts, but it's actually completely accurate. So this is what you would see if you imagine being like a silicon atom inside the silicon crystal, looking up at the ceiling, at the top of the silicon chip. So the blue you see there is the electrons that have been pulled up by the electrodes of the transistor. Okay? And then in red, there is the nucleus of the phosphorus atom, and then the sort of orange lines represent an electric field that controls the charge. So we start from the phosphorus atom ionized. It doesn't have an electron attached to it. And then we grab an electron from that pool of electrons in the transistor in the spin down state, in the low energy state. And then we irradiate it. If we hit the right frequency, the electron will turn up to the high energy state, and then from there it has enough energy to escape. So it escapes back into the transistor, and when it does that, it unlocks a burst of current, which lasts until another electron in the low energy state goes back onto the atom. Now we try and irradiate the atom with a different frequency, which is the one it would respond to if the nucleus would flip the other way. In this animation, we haven't flipped the nucleus, so the electron does not respond, so it does not go to the high energy state, so it does not escape, and so it doesn't give you a current. Okay? So this is a lot of blah blah, but let me show you the real thing. This is the real thing. This is actually the oscilloscope screen in my lab. This is a video I've taken with my phone. Okay? This is what you would see if you came to my laboratory. What you see there is the current through this little transistor. You see there are these periods where there's basically no current. There's a bit of noise, but otherwise it's flat. And now you'll see in a moment, you get these bursts of current. These bursts occur every time you have successfully excited the electron spin. And you see you get a lot of bursts, and then they stop. Why do they stop? Because we flick the nucleus the other way. So now the electrons no longer respond. So now I would like you to ponder on this for a moment, okay? What you are seeing here, You're watching with your own eyes the quantum state of a single electron in real time. There's no, like, this is the real thing. I haven't sped it up or slowed it down. This is what you see in the lab. And also, you're seeing the quantum state of a single nucleus, because you can tell whether there's zero current or a lot of burst, depends on the direction of the nucleus spin. Okay? This is the kind of thing that my quantum mechanics teacher 20 years ago when I was at university taught me cannot be done. People really believe that if you read, old papers by, Einstein and Schrödinger and so on, they say, oh, this is nonsense, this can never be done. We do it every day. It's not because quantum theory itself has changed. Quantum theory is the same for the last 80 years. But it's the quantum technology that has changed. The tools we have to make contact with the quantum world have changed dramatically in the last 20 years. This is what sometimes is called the second quantum revolution. The theory is the same, but the technology is so much further. You can now watch a single quantum object with your eyes every day. Okay, now one more thing about spins, well, about quantum theory, is entanglement. This is the thing that broke Einstein's mind, right? It was the famous spooky action at a distance, and God doesn't play dice and things like this. We now understand it perfectly well, and we've done experiments to show that this is true. And again, it's actually very simple when you accept the symmetry of the world. So if you take two spins, right, they each produce a magnetic field on each other. And so one makes a field this way, and the other one will make a field that way. So they want to point anti-parallel. So they could be this way if you put them side by side, or they could be this way. Which one do they choose? None of them. They are in a superposition of this way and that way. And what that actually means is that each one of the spins doesn't actually point anywhere. So an entangled quantum state is a state where each spin is opposite to the other, but doesn't point anywhere. It sounds really strange when you say it in normal day-to-day words, but it's actually completely normal. In fact, you are full of this stuff. Every covalent chemical bond involves a pair of entangled spins. That's a water molecule. That's 70% of what you are. In every chemical bond between the oxygen and the hydrogen, there is a pair of spins that have that entangled quantum state. There's nothing weird about it. We are all made of this. All right, now let's get to the actual business side of things, which is computers. Okay, that's what you all want to know about. So again, I'm going to take it from the very beginning. That's an old image of an 286 from the 1980s. For those of you who remember that. So let's say you want to do a little calculation. You want to calculate how much is 3 times 5. Computers are digital computers, right? So let's say you use 4 bits, so you say 3 will be 0011 and 5 will be 0101, and the computer will calculate that 3 times 5 is 15, which is 1111 in digital code. Now, as the great Rolf Landauer, one of the fathers of information theory, both classical and quantum, famously said, information is physical. So if I say I have a 0 in my computer, what does that actually mean? That 0 is a physical reality. And the physical reality in all the computers you have in your pocket or on your desk is the voltage across a silicon transistor. Okay? So 0 means low voltage across the terminals. 1 means high voltage across the terminals. It's a physical thing. And by the way, the physical object, so the silicon transistor, is, in my opinion, the highest achievement of humankind. It's much more impressive than going to the moon and back. It's much more impressive than finding the Higgs boson. If you actually go and look at what's in your pocket, there is 1 billion objects, man-made objects, on a scale, on a size scale of a few hundreds of atoms across from end to end. There's 1 billion of them. And they all work. On average, there's 100 broken transistors out of 1 billion transistor chip. And you buy them in the shop for a few dollars. This is the most amazing achievement of humankind. Okay? So I'm going to tell you about quantum computers now, but keep in mind that what we have in our pockets and on our desk is a fantastic feat of technology. But we have other choices, so let's look at what happens if we use, instead of a silicon transistor, a quantum object that has two natural states to encode quantum information. So for example, I could take two protons and one electron. And I say, okay, if the electron is on the left, I call it a 0. If the electron is on the right, I call it a 1. But as we've discussed before, it can also be, in fact, it would like to be usually 0 and 1 at the same time. That's a completely legitimate code on this quantum bit. Another example is the spin, so I can call spin down a 0, spin up a 1. And again, another natural state is the superposition of up and down. Now, this in itself doesn't give you very much. You only start to understand the power of quantum computing when you look at multiple bits. And I'm going to give you an example here. So let's say you have 3 classical bits. Okay, this is a classical case. With 3 bits, you can write 8 numbers, 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1. Okay? 8 numbers, 3 bits. In terms of information, yes, you have 8 choices, but all the information in there is 3 bits of information. I need to give you the first bit, the second bit, and the third bit, 3 bits. Now, let's say I redo the same thing with quantum bits. Let's say I use a spin. That's the thing I use in my lab. So now I always have those 8, we call them basis states, like the 0, 0, 0, 0, 0, 1, and so on. But because spins are quantum objects, I am allowed to make superpositions of all these 8 states. Just like I did a superposition of the spin up and down before, now I can make a superposition of down, 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 with down, down, up, with down, up, down, and so on, all 8 of them. So now, if I want to describe what is the quantum state of those 3 spins, I need 8 numbers. I need to give you the fraction of, it's a little bit of this, a little bit of that, a little bit of that. So that's 8 numbers, where 8 is 2 to the power 3. So if I had 4 quantum bits, I would need 16 numbers. If I had 5, I would need 32 numbers. So in general, if you have n quantum bits, you need 2 to the power n numbers to describe the full quantum state. Now, why is it more than the classical case? So why do I need 8 here and I only need 3 in the classical one? The reason is actually because when you do these kind of superpositions, most of the states you get are entangled states. So you get a lot of those situations where the bits exist only in relation to each other, not in their own individuality. This is something you cannot do on a classical computer, but it is a perfectly legitimate digital code in a quantum computer. It's as if you had a vocabulary that is exponentially richer. And every word is completely legitimate, except you cannot write it on a classical computer. Okay? Now, let's take this to the bigger scale. So that number there is 10 to the 90, so it's 1 with 90 zeros after that. That's more or less how many particles there are in the known universe. Now, 10 to the 90 is about the same as 2 to the power 300. So what that means is that if I had 300 quantum bits that are all perfectly, fully entangled, to describe their quantum state, I would need as many numbers as there are particles in the universe. That's the power of exponentials. Okay? Now let's do something a little bit more concrete, and this is something you may have heard of in the news, like quantum supremacy or quantum advantage. These are actually quite simple. Let's go a little bit smaller. Let's take 50 qubits, 50 quantum bits. So you'll need 2 to the power 50 numbers to describe the quantum state, so the code encoded in those 50 qubits. Now, 2 to the 50 is about the same as 10 to the 15. So imagine you use 1 byte of classical data for every coefficient. So that means you need a petabyte. A petabyte is 1,000 terabytes. And that's something you can kind of visualize. Imagine your typical terabyte hard drive that you have to back up your data. Imagine stacking 1,000 of them here on the stage. So make a little pile. That's a petabyte. Okay? You can kind of visualize that. Now let's go to 70 qubits. so you need 2 to the 70, which is about 10 to the 21. So that's a zettabyte. So that's a billion terabytes. So now you have to imagine a billion of those terabyte hard drives. They will overfill this room. They will overfill probably the convention center. And in fact, that is about as much digital data as there is in the world at the moment. Take everything, like all your laptops, servers, data centers, the whole shebang, that's about a zettabyte of data everywhere. So now you see that if you could make a quantum computer with 70 qubits that are all fully talking to each other and entangled with each other, and you could run a calculation on this computer that uses the entire 2 to the power 70 information content of the computer, you could legitimately say that you've done something that cannot, under any circumstance, be done on a classical computer. Now, this is a very oversimplified argument, but it gets the numbers more or less right. So you may have heard, Google is now, they got a 72-qubit prototype. They're kind of reaching that scale. That's where we're at. This is the scale where you can legitimately say we're doing something that cannot, even in principle, be done on a classical computer. This is about to happen, so stay tuned. Now, what do you use this for? Okay, what are the applications of quantum computers? And I'm going to give you, again, because I like doing things simple, a simple example of the kind of problems that quantum computers are good at solving. They're the ones where the computational complexity explodes exponentially. That's what they're good at. So here's an example of a combinatorial problem. Let's say you have 2 eggs and a 6-pack of eggs. How many different ways can you put 2 eggs in a 6-pack? So for the first egg, you've got 6 choices. For the second egg, you've only got 5 choices because one you've plugged before. And then if the 2 eggs, you consider them identical, it means you can swap them around and get the same configuration. So you divide by 2. So in total, you got 15 different ways to put 2 eggs in a 6-pack. If you do 4 eggs in a 12-pack, now you got 12 choices for the first one, 11 for the second, 10 for the third, 9 for the fourth, and then you have to divide by the number of permutation of 4 eggs, which is 4 times 3 times 2. So that's 495 choices of how to put 4 eggs in a 12-pack. So it goes up pretty quickly. And then I have a friend who works in a cafe around here, and so I asked her to take a picture of 20 eggs in a 30-pack, the stuff they have there in a cafe. And so you do the same number calculation there, and you get 30 millions. So you see how the complexity of this problem absolutely explodes as soon as you start to make it bigger. Now, this is not the kind of problem you want to solve on a quantum computer as such, but I give it as a sort of metaphor of the problem of quantum chemistry and molecular simulations. So let's say, you've seen these images of, atomic orbitals and electrons in there. So you can kind of imagine that the electron is like an egg, and the orbitals of the atom or the molecule are like the pack of eggs. So what you're trying to do when you do molecular chemistry and quantum chemistry is trying to figure out what is the configuration of electrons that has the lowest energy, so the one that is most stable. And so I hope that my little, cafeteria example gave you a sense of how complex this is. There are so many different configurations, even just with a few orbitals, right? So here's an example that's been done very recently at IBM, in fact. It's a very simple molecule. It's called beryllium hydride. It's one beryllium atom, which is element number 4, so it's got 4 electrons, and 2 hydrogen atoms. Very simple molecule. So it's 6 electrons in total. Now, for reasons I won't go into, if you actually did the full quantum mechanical calculation of the energies of each one of the possible configurations of the electrons in this molecule, you would have to solve a 40,000 by 40,000 matrix. This can be done, but it's a heavy calculation already. So what people have done at IBM is that they've done kind of the eggs in a carton example I've shown to you. So they've mapped each electron onto one of their quantum bits. This is a processor with 7 quantum bits. They only use 6 out of 7, in fact. So each one of the 6 electrons is one of the quantum bits. And then they arrange the interactions between these quantum bits in a way that resembles the interactions between the electrons in the beryllium hydride molecule. And then they get essentially a result. So the configurations of these quantum bits tells you, maps directly on the most convenient configuration of electrons in the molecule. Okay? So instead of solving a 40,000 by 40,000 matrix, you just run a 7-qubit quantum computer. Okay? Now that's for a useless molecule, beryllium hydride. No one cares about it. But let's say you go to something like this. This is actually, again, a simple molecule. It's penicillin. It's one of the simplest, drugs. This would be completely out of the question for a classical computer. You could never solve this exactly. There are, in fairness, some very good approximation methods that people in quantum chemistry use to get a sense of what goes on here. But fundamentally, the reason why you cannot just go on a computer and design a drug that does something for you is because that problem is computationally intractable. It's just way too hard because it's a quantum problem, because it's the problem of the quantum mechanical lowest energy state of a small, but it doesn't need to be that big to be already intractable, number of quantum particles. So this is one of the hopes we have, the nearest term applications of quantum computing is for drugs and molecular design and material design and so on. So problems that are intrinsically quantum that easily become intractable on a classical computer, and then the quantum computer is sort of the natural platform to address them. So these are problems with, of course, very big impact in society and in business. Let's look at another, actually really simple molecule, ammonia. 1 nitrogen, 3 hydrogens. So simple and innocuous. But ammonia is what's used for fertilizers. So we would not have 7 billion people on Earth if we didn't have a way to make ammonia for fertilizers to feed the world. Except the production of ammonia consumes about 2% of the world's energy. That's an ammonia plant in India. It's a very inefficient process. It requires very high temperatures, high pressure, it's slow. It burns a lot of energy to make ammonia. Of course, we need it, so it's energy well spent. But you think, isn't there a better way? And you might think, well, maybe there isn't a better way. Maybe that's just what you need to do to make ammonia. But we know it's not true. There are bacteria that spontaneously produce ammonia without having to heat up to 600 degrees. So we know that there is a way, but we haven't found it. Why haven't we found it? Because it's a quantum process. That chemical reaction that goes on inside that cyanobacterium is a series of quantum evolutions. And we just can't make sense of them on a classical computer. So we hope that quantum computers will be able to resolve these kind of really impactful and important problems in science and in economy. All right, another example which I don't think is going to change the world as such because it doesn't go from exponential complexity to polynomial, but is the database search. So this is one of the very first quantum algorithms that was discovered by Grover in 1996. So if you take an unsorted database, so let's say I gave you a telephone book and I told you, I have this number, can you find whose number this is? The numbers are not in order, and there is no better classical algorithm than just scrolling through the whole book until you find the number and you find the name. In a quantum database, you can prepare a superposition of all the entries in the database, and you can arrive at the result in the square root of the number of entries. So if you had a million, let's say the Sydney telephone book with 1 million names in it, on average you need 500,000 checks until you find the number. On a quantum computer, you need 1,000 checks. It's nice. Okay, and I have a video on YouTube if you're interested. It's called Quantum Computing Concepts. They're 3-minute short videos, and in one of them I explain the quantum search algorithm. All right. Now, this is all what you've all been waiting for, factoring, right? You guys work in the finance industry. You have, data that is precious, that needs to be encrypted and be kept safe. And you've probably heard that a quantum computer can crack classical encryption because it reduces the complexity, the computational complexity of finding the prime factors of a composite number from exponential to polynomial. Okay? So it turns an intractable computation into a tractable one. So this is really what most of the finance and defense and government agencies are interested in, because that's the one that can have a massive impact, in theory. Now, let's get to the practice. Nothing in the world is perfect, right? So in a computer, in fact, yes, there are the bits you're trying to calculate, but there's actually a lot of redundancy, because you need to have the ability to detect and correct errors. So usually, for example, when you transmit a bit of information, you don't transmit that bit of information. You may transmit 3 copies of it, so that if there is an error along the line, and you get, one bit is 1 and the other 2 are 0, you can say, well, that was probably a 0. It should have been 0, 0, 0, and then there was a mistake, and you flick it back. You can do something similar with some caveats in a quantum computer. So you encode, instead of on 1 bit, on 3 bits. And so the single bit of information we call the physical qubit, and the encoded in many physical qubits bit of information is called the logical qubit. Okay? And so people have invented some very efficient methods to do large-scale quantum computations on 2-dimensional grids of qubits. And so this kind of code, an error-correcting code, has a tolerance of about 1%. So it can correct errors as long as they occur less than 1% of the time, which is very good. And so on average, you would need, but if you go below the threshold, you need less redundancy. So people normally look at, let's say, 0.1% error. You need 3,600 physical qubits per logical qubit. Okay? So now let's look at what it means in practice to find the prime factors of a number. Let's say you get a 2,000 bits number, and that is the product of 2 smaller numbers that are some cryptographic keys you want, and you want to crack that cryptographic thing. So you'll need twice that in logical qubits, so 4,000. Let's say you got 0.1% error rate. You need 3,600 physical qubits per logical qubit, so it's about 20 million physical qubits. And then there's something I won't go into. You need another 200 million qubits for other stuff. Just believe me. Let's say you have a 100 nanosecond clock cycle, which is pretty good. It would be state of the art. That means you need 220 million physical qubits, and it will take a day to do this calculation. Okay? So as I said before, we are now kind of racing at the 50, 70 qubit level. So this is to say that quantum decryption is not around the corner. It's really not around the corner. It will take us a while before we get there. But at the same time, there are motivations why you may want to start being interested in that, because, of course, someone could capture your communications, store them on a hard drive, and then 20 years from now, crack them. So depending on the sensitivity of the data you're handling, you may want to start caring about this. And many people are starting already, which is a good idea. I have to say also, in defense of the quantum technologies, the quantum technology can also be used for good. So you can use quantum encryption to protect your data. This is actually a slide from a company here in Australia called Quintessence Lab, and they offer a suite of technologies like quantum key communication, quantum encryption. So these things actually exist, and in fairness, they are much more advanced than the quantum computing itself. So one thing I'd like you to take home is that quantum safety is actually much more advanced than quantum danger. Okay, so we are on your side. Okay? Now, what does a quantum computer look like? These are 3 examples. The one on the left is actually my chip from my lab. It's a small silicon chip on a printed circuit board. The one in the middle is an IBM 5-qubit superconducting quantum computer. The one on the right is an ion trap quantum computer from Austria. And the scale of these objects is about 1 millimeter for my chip, 1 centimeter for the IBM chip, and 10 centimeter for the ion trap vacuum chamber. So this seems like innocent, but then you say, but wait a minute. These things, for example, my little chip is mounted into a giant, it's like 2 by 2 by 3 meters thing that cools it down to near absolute zero, right? And also the ion trap, there's a trap there, but then there's this massive optical table that's as big as this stage that's got lasers and lenses. And so an objection you often hear is that, how am I going to put that monstrosity in my office? It's never going to work. Of course, the point is that you're thinking of a classical computer as being a laptop like this, which is not the case, of course. A classical computer is this. It's a data center. There's hardly anything you do nowadays that actually takes place in your computer. It takes place in some data center. And so in that data center, if you now put to scale my giant refrigerator, it's actually looking like this. So what we envisage is that there will be data centers that will have additional, quantum rooms with machines like this, and you will connect to them remotely, possibly with a quantum secure connection, and then you can get quantum calculations done there, and you just, from your own normal laptop. Now, I just want to say one thing, because my background is in low temperature physics. Reaching these low temperatures is actually probably the only achievement of mankind where we can legitimately say we have beaten nature. So if you go into empty interstellar space, in outer space, the temperature there is 2.7 degrees of absolute zero because of the microwave cosmic background radiation. Whereas in my lab, we get 0.01 degrees. So we've done something that nature just doesn't do. And we use it to make our quantum computer work. All right, so last thing, so we have a little bit of time for questions. So my activity here is to build quantum computers using silicon. I told you before that silicon microchips are, in fact, the most amazing achievement of humankind. So the idea was, can we readapt these incredible technologies, a $1 trillion industry making these chips, to make quantum computers? So what you see on the left is actually a fairly obsolete, from 10 years ago, 45 nanometer node silicon transistor. What you see on the right is a quantum bit, 2-qubit device made by my student a couple of months ago. And I mean, that's a cross section. The one is a thing from above. But actually, these things are quite similar. They have basically the same size, and they're made with the same technology. I mean, if anything, the technology I use is much more primitive. I don't have, of course, the facilities of an Intel factory, right? I mean, I'm working in a university research lab. But so with this kind of technology, we have, in fact, achieved the longest quantum memory time of anything in the solid state using these phosphorus atoms. So this stuff works really well. And we are now developing new technologies, new schemes to make that, remember that two-dimensional grid I showed you before, the surface code, to actually have these atoms on a two-dimensional grid and operate them in order to perform large-scale quantum computation. So this is an ongoing project. We're doing very well here in Australia, and there's other people around the world also racing with us. But it's a good, healthy race. So with this, I'm going to finish. I just want to re-highlight a few key messages that I would like you to take home. First of all is that quantum mechanics is just the way things are, okay? Don't let anyone tell you that, oh, it's this weird, spooky, counterintuitive stuff. No, it's just the way things are. You are a quantum object. We all are. Everything is quantum, okay? And in fact, it's got great potential for novel technologies. We can do things with the quantum property of particles that are very useful. Quantum information is exponentially more dense than classical information. So if we can find a way to exploit it, we can crack problems that are otherwise completely intractable. But please keep in mind that it's not easy to find the right kind of algorithm that actually exploits all that exponential computing power. Okay? So there's only a few examples known so far. And finally, that quantum computers need not be a completely different object from what you're used to. In fact, people like myself and some other colleagues are building quantum computers using the same technology that's used to make the computers you have nowadays. So with this, I'm finished. I'm happy to take questions.